Okay, so we have spent 2 minutes waiting for everyone to join. So I think we're ready to start. Thank you for joining this webinar. My name is Juan Fraire. I am from Cloud&Heat, consultant from Cloud&Heat. And today we're going to be discussing containerizing machine learning applications. I'm going to discuss a little bit what machine learning is about. I want to introduce the concepts. I want everyone to be on sync on what machine learning is and how we can implement simple machine learning applications. So my objective of today is to finalize this webinar in such a way that we know which is the data pipeline or which is the overall workflow that is required for building an end-to-end machine learning application. And then we're going to also discuss briefly how can we containerize this and what are the challenges that we should be taking care of, and how can we actually leverage some of the state-of-the-art infrastructure products such as those that offers Cloud&Heat offers, so that we can profit from let's say, from a robust and performant machine learning deployment. So what is this webinar about? So as I mentioned, this webinar is about machine learning. We are going to spend around 70% of the next hour talking about machine learning concepts. With this, basically, this is a disclaimer saying that I expect the audience not to know basically anything about machine learning. So you don't need to be any expert whatsoever. We are going to start from scratch on machine learning concepts. And then we're going to spend around 30% of the webinar talking about containers and how these containers can be orchestrated. And in particular, we are going to explore this containerization concept from a machine learning point of view. I want to say that this is a hands-on, step-by-step, beginner to level tutorial. We're going to not only be introducing the concepts of machine learning and container, but we're going to be running on real time some real code implementing these concepts. I want to give a feeling that there are actually a lot of tools in Python in particular that makes machine learning quite easy to implement, not necessarily easy to understand what's happening under the hood, but is something that we can spend some minutes looking at some code in this webinar, in this hour or something else webinar, to take a look at how a machine learning application is actually built. So even though I do not expect the audience to be any expert or have some previous knowledge on machine learning nor on containerization either, some Python, let's say, understanding can play in your advantage, so you can basically quickly understand what's happening on the code that I'm going to present today. But anyway, Python is also quite easy to read, so if you're not a programmer, I think that we can make it through anyway, and trust me, the idea that they want to trust me today. So please feel free to leave questions on the chat window during the talk. If we eventually make a few seconds pause, I can take a look at that and try to answer the questions on the fly. Otherwise, depending on how the flow goes today, I will basically tackle those at the end of the webinar. Another comment is that we are recording this as we speak. And this will also, naturally, this will be made available offline. So if any one of you needs to drop and continue this later, you will have this material also for later consultation. So I hope this is fine for you. And if these are basically what this webinar is about and how we are going to spend the next hour together here. So let me start spending a few words about Cloud&Heat. So Cloud&Heat is a full stack data center provider located in Dresden, Germany, beautiful city, by the way. So Cloud&Heat is specialized on basically a single aspect of computer center, of data center, which is water cooling solution, and water cooling solutions as a mean to go for a smart reutilization or reusing of the energy that of the heat that is produced in a data center. There are a lot of water cooling solutions, but Cloud&Heat actually is quite unique in the sense that the company follows the visions that the computing processing is actually a means for transforming energy, actually. So for transforming electrical energy into heat that can be used in concrete applications, such as building, heating, or maybe power plant as well. So this is the vision of Cloud&Heat, and we're going to discuss this a little bit later as well, of the distributed data center vision that comes out or derives from this heat utilization vision. Actually favors some quite interesting state-of-the-art challenges for data center technologies. Actually, this is Cloud&Heat actually owns a distributed data center which is located with computer nodes located on Dresden and also on Frankfurt, among other places on Germany. And this distributed data center is currently based fully on OpenStack, which is an open source software framework for controlling and operating these data centers. Not to mention, Cloud&Heat has several certifications of quality and processes, and also has received some quite notable rewards on terms of one of the most successful startup company in Germany and Europe as well. So about me, I am a consultant at Cloud&Heat. I'm actually based in Argentina at this moment, so I'm the point of contact of Cloud&Heat in South America at the moment. But I'm also an applied science PhD, and I do research and teaching mostly on computer science, which actually motivates my cooperation with Cloud&Heat, and also motivates the webinar I'm here to present today. In Cloud&Heat since 2019. And since then, I've been mostly involved in designing interfaces and computer science techniques to operate a distributed data center, as I mentioned. Recently, I'm mostly starting to focus on Managed Kubernetes, which is one of the products that I'm going to briefly discuss toward the end of the presentation today, which is a perfect fit for machine learning applications, which is what we're going to discuss today as well. So I leave my email here. I will also repeat my email in the end. So please feel free to reach me or contact me any doubt or any question I can help with. So this is, I don't like to talk too much about me, so we'll just skip this and continue to the interesting part of the webinar. So how is this presentation organized? So basically, we're going to go through two sections. As I mentioned, we're going to spend around 70% of the talk talking about machine learning. I really want the audience to understand what machine learning is. Machine learning is nowadays like everywhere, being mentioned for everything, and every application seems to use machine learning today. But I want to understand I want us to understand what are the principles of machine learning, what are the bases, the foundational concepts. So to this end, as I mentioned, we're going to go through a hands-on example of a machine learning application. We're going to be focusing on the training phase in this part. We're going to see what training means and so on. As I mentioned, the idea is for you to get an idea of what is the overall flow of the process in a machine learning application. And then on the second part of talk, we're going to go into the details of how can we containerize this machine learning application. We're going to briefly comment on what containers are and what is a container orchestration technology. So we're going to briefly go into these concepts, and we're going to see how easy it can be to containerize a machine learning web service. It's a very simple example that we're going to follow, but still is representative for understanding what it takes to have a machine learning service running on the cloud. And then we're going to discuss some outlook aspects, in the sense that we're going to discuss what are the challenges for larger machine learning applications, and how, let's say, modern infrastructures technology are actually evolving also to support what are current and future trends in machine learning. So let's start with the first part and get our hands dirty a little bit on machine learning. So this is like a typical introduction slide for machine learning, and this slide actually goes into mention actually three other names that are surrounding, or let's say typically comes together with machine learning, but they actually mean some slightly different things, even though they're somehow and sometimes used interchangeably. So the broader, let's say, concepts, and likely the older one also, the most let's say, was introduced several years ago, and I don't want to be mistaken about this, but this is something like around 1950 or something like that. So it's really old. It's a concept of artificial intelligence, and artificial intelligence, there are so many different definitions for what this is, but we can safely say that an AI program is an AI is a science or a discipline that basically try to study programs that can take creative decisions, in the sense that these are not programs that are just input and output that has defined structure and so on, but also have some freedom in order to make decisions, in order to create some new behavior or new, let's say, solutions that than what were the program originally. Okay, so it's like really a broad concept, and so as I mentioned, it's quite old. But we're going to be looking at a specific type of AI, which is machine learning. Machine learning is a sub class or a sub area of artificial intelligence, where machine learning is defined as a branch that can learn from experience, and this is like what makes machine learning so particular, because machine learning can use data or use measurements or use observations from real life in order to and incorporate this into abstract or abstractions into the program itself, and use these abstractions to take decisions or to make any particular processes. So machine learning is a subtype of artificial intelligence where we are focused on learning, of getting data of observation and taking this data into an abstraction into our models. And we can see here on the right-hand side of the slide some, let's say, image that can actually somehow illustrate what I'm trying to say. So maybe we can say that an observation from real can be an image, let's say it's an array of pixels, for instance, in this case. And a machine learning application would typically try to abstract information out of this data. One way of doing this is just by processing these images into different parts, and then also from each of different parts execute some filterings and so on, so that we can detect edges, for instance, from a face in this case, for example. And then this abstraction can somehow be processed as well, and we can combine this abstraction into parts. For instance, we can detect what is an eye or a mouth or a nose from the image that we're processing by the application. And we can somehow create abstractions, even higher level abstractions for objects, such as faces and so on, and eventually allow our program to have a data structure that can actually be mapped to the observation that we are taking from reality. So somehow this seems somehow like a science fiction, but we're going to see that in the end is somehow quite, let's say, rustic in the sense of how this actually works in the end. And within the machine learning domain, we should mention deep learning. Deep learning is what's basically brought machine learning and artificial intelligence back to the attention of everyone in the world, mostly pushed by Google and image recognition. But deep learning is a little bit more than that. And deep learning is the branch of machine learning that actually uses neuronal structures based on the brain structure of human. So these also biologists, I have friends that are biologists that are quite unhappy about this simplification of the human brain, but still true that it is somehow there is like an inspiration in this. And basically we're going to see in detail what this is. But the deep learning models actually are layers of simple neurons that abstract the information more and more as this layer evolves in abstraction. And we are able to go higher and higher in this abstraction path that I'm showing here on the right. So we are going to be talking about these deep learning techniques and how these neural networks actually allows us to play with this abstraction and create some real useful machine learning programs. So what is learning after all? We're talking about learning, and something interesting to see about learning is that how this is different from traditional computer science programming or traditional programming in computer. So if we take a look at this image here on the right, when we write a program for something, let's say like a web application or whatever, what we typically do is that we know the shape of the input data, right? We know the shape of the output data, and we just write a program that transforms this input data into an output data. This is like the traditional computer or informatics approach, where you write a program, you have some requirements, you know what is the function that you need to create in such a way that the output data is what you expect to be based on an input data. So this is like a general way of programming. Machine learning, or the learning concept in computer science, is a bit different. The learning in computer science actually states that we do not know how this function is like. So namely, we cannot specify our requirements on how this function should be for executing our program. And this is where machine learning comes into play. Machine learning is all about guessing this function based on the input data and output data. And this is very powerful because instead of, let's say, hiring hundreds of programmers in such a way that we can parse and, let's say, interpret images, and based on that parsing, specific parsing, take some decision whether if this is a face of a human or a dog or a plane, then machine learning takes care of the processes of discovering automatically which is this function that maps the input and the output data. So this is what makes learning so powerful in machine learning, because this is a very generic approach that can be used for any data set or almost any data set without a further specification of how this function looks like. So we're going to see that this function here in the middle are basically models. We're going to be deriving models for this, and this is what all machine learning is about. We're going to be talking about supervised machine learning, in the sense that supervised is the machine learning approach where we do already have a good data set of input data and output data. And based on that set, we can basically run over and over that data set and derive this function that we have here. Unsupervised, which is the opposite to supervised, is also somehow present in machine learning. But we are not talking any longer about training here, but rather about some reinforced learning, which is maybe a material for another talk. We're going to be talking about supervised machine learning applications today. And two important classifications that we can mention at this point is that this function that we have here basically depends naturally on what's the output data that we want to get. And output data can be basically of two types. One of them is regression, in the sense that the output data is just a number that we want to get. So let's say, for instance, a probability. Let's say, for instance, I don't know, the expected duration of a given event, right? So this is a continuous number that we want to get in the output data. So this is a continuous variable that we're trying to guess, that we're trying to predict in the output data. And there is another family from machine learning applications which is quite different, which is a classification function, where in the output data, what we want to get is basically, this is a dog, this is a cat, this is a human, right? So these are discrete values. These are variables which are discrete and can have either one or another value. These are two different families that we want to keep in mind that exist in machine learning. So, and training is all about finding this golden function in the middle that maps the input data and the output data. And one way of visualizing this is by, let's assume that this function is a linear function, like the one we're showing here. So f is basically an f of x that takes x as an input, where x is the input data. And this x is basically part of an equation where this is multiplied by a weight, number one in this case, which can be like the slope of this linear equation. And then we can add a second weight, which we're going to see that's called bias as well, which basically is the y component of this line of the linear equation that we have here. The thing is that if we somehow guess on the first place that this function that we're looking for here can be represented by a linear equation like the one we have here, then having this machine learning application running for us is just a matter of understanding which are the weight number one and weight number two that best perform in terms of mapping input data and output data. So for every X that we're having on the input data, basically we get a very good estimation or prediction of what the Y is going to be in the output. And this is basically obtained by having very good estimations of what are these two weights of the equation here. So the way of determining this weight is what's called training. And training is somehow in machine learning, also this is what I mentioned earlier today, is somehow quite rustic in the sense that there is, at the first glance, this looks like basically like best efforts or brute efforts, trial and error, in the sense that we are going to vary this weight and change them randomly, for instance, and keep random like in between parentheses here, and we're going to try a lot of this weight. And for each of these weight, we're going to try the output data that we get, and we're going to see how good this output data or how far is that output data from what I expecting to see. And based on this trial and error, we're going to try to estimate these two weights in such a way that we can learn this function here, or we can understand which is this function here that executes the process that we want to. And this is what's called training. It's actually not so much, it's not really stupid, just trial and error, but there is some very, let's say, sophisticated intelligence behind how can we actually look for this weight in a very intelligent way, such that we search and we try to converge on the best weight that actually, let's say, makes this function as close to the model, to the real model that we want to. So in this, for feeding and for guiding this intelligent search of parameters of weight, in this case, we are going to be using error functions or loss functions, which is a way of measuring how far the output data that we're getting is from the real output data that we want to get, right? And based on this loss function, we're going to try to minimize this loss function in such a way that the model that we're getting in F is actually as close to the reality that are possible. Something interesting about these training techniques is that they can be stopped anytime, right? So naturally, the longer they run, the more precise that these weights can get, right? So therefore, the more precise the predictions that our model can do. But we in principle can stop that at any time, right? And once we have this model trained, we naturally, something I didn't mention is that for getting this trained and for getting and studying the output data for each of these trial and error passes, we need a lot of data just to validate that this model actually performs okay for all input data and not just one or two or three samples of the input data, but all of them. So once we have this model trained, it is expected that new data that follows the same pattern that the input data was already there can be used as input, and therefore new output data can be predicted in the end, right? So therefore, we can say that if we complete this training process successfully, then we will have an abstraction, an abstract model here in the middle that is going to be able to mimic the phenomena that we are basically measuring and observing on these input data and output data sets. So where does the neuron part come into play? Well, the neuron is one way of presenting this intermediate function here that we have in the middle. Instead of using just a linear equation as we did in the previous slide, we can try to incorporate a more sophisticated model of function here, which is a little bit more complex and therefore can model a little bit more of complex phenomena as well. And a neuron shape has something to do like this. And if you take a look, this is where the neuron part comes into play, and somehow it has the aspect or the feeling of what's a real neuron in biology. The neuron basically, as we can see here, it can take several inputs. It can take several inputs, but it can take also one. I'm just plotting 3 here just as an example. But it has a single output, okay? And each one of these inputs has a weight. So again, we're just recovering also the weight terminology that we were using previously. And also the neuron itself has an internal weight that is sometimes called bias. This is in the end, the equation that we end up having at this point is a linear, for instance, combination of the inputs, of the weighted input. Okay, so each input is multiplied by the corresponding weight. And then we also have this bias element in the end, which is very similar to what we were seeing for the linear function, actually, which is the bias of the neuron itself. In general, this input weight, which is the weight vector that multiplied the input signals, are known as kernel. And this internal weight in the neuron is known as bias. We're going to be recovering this terminology in the next minutes as well. And this weighted sum that we have here is typically provided as input in an activation function. So if we don't have any activation function, then this is just a linear function, and it's essentially the same that what we saw in the simple example before. But in order to model more complex phenomena, it is known that if we have some activation function that somehow brings the output of the neuron to the extreme and makes this neuron very sensitive to the combination of the input parameters, then we can model more complex phenomena. We're going to see this in a little bit more in details in the next slides. But it's just to understand that typically this activation output is typically close to the extremes, and which extremes I'm referring to a very narrow range of number, ranging from 0 to 1 or -1 to 1, depending on the neuron configuration. But typically this output signal here is going to be very close to 0 or very close to 1 or very close to -1 or very close to 1, which is also somehow inspired on how neuron should work at least in biology. And this is the terminology that is used is whether the neuron fires or not, basically. So what's interesting about neurons is that we can connect them and create a network of these neurons. And this can gets a little bit now more complicated. This is just not just a simple linear equation that you want to solve, but you can get like an arbitrary complex combination of this neuron. In this example, what I'm plotting here is like a multi-layer set of neurons, which is what's typically used in machine learning, in such a way that we have some neurons that takes the input signals, and these signals are propagated through to a second layer, which is also known as hidden layer, because there is no way to, let's say, directly access this layer that we have here in the middle. This is why it is called a hidden layer. And this propagation of the signal is actually modified by a weight as well here, each one of them, and the bias of the hidden layer neurons as well. And this process repeats throughout layers, and as far as we approach what's called the output layer, which is this one here, that basically each neuron behaves exactly like each other, right? So it's just basically within each layer, each neuron behaves like each other, and it's just an instantiation of these neurons that happens to create this neural network structure. And in this case, we have a single output. For each output neuron that we have a single output, and we can have many outputs in this case, right? So just in this example, we're having only one. And we end up having like a more complex model structure or the function that we're trying to guess. And this is way more complex in the sense that we have, for instance, this very example case, we have 21 parameters to guess or to find or to fine tune such that the model that we have here actually delivers the prediction that we want to create in this case. And in the end, this array or this vector of weight that we're seeing here, which 21 elements, is actually encoding the knowledge of the model that we want to that we're looking for. This is what actually is really valuable for the model. So not only the structure of the model as we can see here, but also these red parameters or this weight that we have here actually encode how they say the software between quotes of this model that we're trying to guess. So this type of structure that we're seeing here is an example of a multi-layer perceptron. This is how they are called. This densely connected multi-layer model of neural networks. There are others, but basically these are known as traditional feed-forward networks in the sense that basically this is a layer, let's say a layer after layer of processing of information flow in this neural network structure. But as I mentioned, there are others. And one of the key aspects of machine learning is determining which is the optimal neural network architecture that we want to use, such a way that this function that mimics the real phenomena actually performs in an optimal way. So key questions that need to be solved in a machine learning application is how many layers are we actually going to use? Which is the activation function that each of these neurons are going to use? How much neurons are we actually expecting to see on each layer? How is this network connected? Are we having a densely connected network? Only a few neurons are going to be connected. So these are all possibilities. And we can see here on the right, like there are a lot of families of neural networks, and the families actually depends on which is the final application that we're going to use for this machine learning neural network structure. We saw that actually the example that we saw before is a feed-forward neural network, somehow like similar to what we can see in this architecture here. But we can see that things can get very easily much more complicated in terms of connectivity, in terms of type of network. So just to mention a few, we can see that recurrent neural networks are actually a specific type of structure where neurons are actually have some, let's say, a feedback loop here, that the output of this neuron is actually considered, again, an input. And this basically is somehow mimics what can be like a memory in a network, right? Because the output is again considering the input. So every successful, every subsequent, let's say, guess or prediction made by the model actually will consider the previous measurements or the previous prediction. So as you can imagine, for instance, this type of memory structures are very good for, let's say, speech modeling, for instance, where the words and letters that comes in a speech or language actually depends on the previous measurements and so on. So you can see that actually depending on the applications, the architecture can be really, really different. And this is where the knowledge of the data scientist actually comes into play. And it's very important to define the right architecture for the neural network that we want to use. So, but I don't want to just to be talking about, let's say, abstract. I want to show very briefly how this actually looks like in code. So we're going to be using Keras. Keras is a Python library. Actually, it's an interface, to be more honest, that can be used to build, train, and use these neural networks that we have been talking about in the previous slide. Keras is open source and free to use. So it's freely available and everyone can use it, and runs on top of TensorFlow. TensorFlow is, let's say, like the machine learning child of Google basically in the artificial intelligence world. The issue with TensorFlow is that somehow it's too much detail and somehow difficult to understand what's happening. You need to be like, the learning curve for TensorFlow is quite steep. So this is why Keras is basically put on top of TensorFlow and facilitates the creation of simple neural networks such as the one that we're going to show today. And we can take a brief look at this in just a few minutes. Both are supported by Google. They have really extensive support for quite an heterogeneous underlying hardware. In particular, we're going to see that despite we can use CPUs naturally for processing the training and the predictions, we're going to see that particularly training is a quite compute-intensive process that can be easily parallelized. And this is where graphical processing units, or GPU, can be a very good support for training machine learning applications. And therefore, TensorFlow actually connects to GPU via CUDA, for instance, which is the NVIDIA library for accesses these many core or multiple core architectures typically available on a GPU. And we are typically going to see that GPUs are equipped with in the order of hundreds or thousands of cores against 8 or maybe 16 cores in a traditional CPU. So even though the GPU's cores are much simpler and, let's say, and less performant than a CPU core, the massive parallelism that they offer is really suitable for enhancing the training flow of machine learning. So without further ado, let's go and then take a look at how this code looks like. How can we start to get our hands dirty into machine learning applications? Let me just switch my screen now to my code here. So I'm going to be using Visual Studio Code now. I will share also in the post of this webinar some material that we already have published for setting up the environment for Visual Studio Code, so that you can also set up this quite easily. Now what I want to just focus on what's the aspect of the code, so that you can follow what can be done in terms of machine learning. So I have this model.py file open here. And it's not a long file. We're going to follow this step by step to see how can we actually create this neural network, how can we configure this, how can we train it, and how can we use it to make predictions. So to start, the first step, the very first step of any machine learning process is getting our hands into the data set. Data in machine learning is everything, and this can be, even though it's a very simple line of code, as we're going to see here, getting these data sets properly set up and configured can take most of the effort of any machine learning application. So in this case, I'm using housing in data sets. I'm just going to open this just so we know what we are looking at here. If we see this housing.data file that I'm using, it's just a huge set of number that if you take a look at this, it makes almost no sense. But for a neural network, this is just perfect. And what we are getting in this housing.data is actually some data gathered in Boston, in the United States, for housing values depending on the very different variables. So I'm going to scroll down here slowly. And this table actually has different columns with information. And for instance, we're going to be focusing on the column, on the age column, which is the proportion of units which were built prior to 1940. So somehow this is an indication of the age of the house. And we're going to be looking at the median value of the house expressed in thousands of dollars, okay? And we're going to try to make some model based on, depending on the age, how does the value of the housing changes and varies based on the data set that we have here. So you can play this afterwards on your own, and you can also include some other variables in the middle, but we're just going to use these two for sake of practice and keep this simple as much as possible. So back to my model.py file here. We are just using pandas. Pandas is a library for data parsing and processing, right? Not going to go into details for now, but what we do need to understand is that we're just basically getting this housing.data file I've just shown with all the numbers and the columns, and getting this into a data frame from pandas. This is we're just reading this file, and we are interested in the, as I mentioned, in the two columns. So age and median price, which are columns 7 and 14, basically. So this is now numbers start from 0 here. So we are just parsing these two columns and getting this into our Panda file. So just something that is quite useful to do is just go step by step and just print and make sure that everything is going okay. So just going to parse this data and print the data and just terminate the program just to see what happens here. So if I do this, we can see that we are, this is the output here on the lower part, and we are seeing that we have a total of 505 samples of data age and data price and house price, okay? So we have samples here already with us loaded in a pandas frame, which is the first step of getting this machine learning application to work. So I'm just going to comment this print command here, and we're going to continue and see what happens next. So something very important is that once we have the data with us, and is to try to visualize this as much as possible. And this is the second point is specific for me here to mention and transmit the idea that it's a very good idea to visualize as much as possible the things that we're going to measure. So in this second step, I'm using matplotlib to plot these two variables that we've seen so we can have a good feeling of how do they look like. And this is a very simple command for doing this. And we see that here on the x-axis, we have this age parameter. And then on the y-axis, we have this median value of the housing data. And these are the whole data set, the whole 500 samples of the data set, how they are distributed in this space. So this is just to have some intuitions. Well, we can see here that naturally, as the age gets higher, the median value of the houses tend to be lower, right? But not so much. So what would be an objective for us is to create a model based on this data, such a way that we can predict some other ages in an accurate manner, okay? So I'm just closing this. I'm going to use matplotlib later also to plot some further results. So third step is, this is where Keras come into play. So first of all, we're going to import Keras, and we're going to import what is a sequential model in Keras. The sequential model in Keras is just a sequential ordering of layers of neurons, just as the example that we have seen on the slides before, right? So it's just imagine this as a train or an array of layers, one after the other, connected in a particular way, right? So this is a sequential model, and most of the machine learning models in Keras can be modeled by a sequential model. So this is kind of a recipe you can see for at least for the first years of data scientists that follows after this. So once we have this model identified as sequential, then the next step is actually to configure the layers. And this is where we need to get a little bit more in detail and take one moment to take a look at how do we actually configure the layers. And it's very simple. Actually, the command to add layer is just basically the same model that we have created earlier. We can just call an add function. And to that add function, we just passed a new dense layer object. I'm going to switch back to the slide so we can talk a little bit more about what's happening here. So let me switch back to my presentation. And let me move this to provide you some context of what's happening here. So we're starting to use the Keras API. This is the application programming interfaces to accessing Keras library. And the sequential, we're talking about model, and we're talking about a sequential API. This is where we're talking a plain stack an array of layers. And the way of adding this layer in a sequential model is twofold. One of them is just to use the constructor, right? So it's the same constructor of the model. When we create the model as sequential, we can just pass as argument the array of layer that we are interested in using. Or we can do what we are doing in the example I'm using now, which is I'm using the add function in the model and just adding a layer on step by step, basically, one layer after the other. We're going to be using dense layer. There are other types of layers, but dense comes from, the naming comes from the fact that every neuron is connected to the other layers, basically. And this is why these layers are known as dense layer. And the first argument that takes this dense layer creation part is the number of neurons that this layer is going to have. So it's really straightforward to what we have seen previously. And then an activation function is configured for this layer, right? So what we're going to see is that we're going to jump back to the code now. And we are saying that we want our model to have once this layer with an output dimension, namely the number of neurons, equal to 1. And then we're going to have an input shape, which is basically what's the inputs look like for this layer, and is how many variables are we going to provide as input. And in this case, it's a tuple where have only one element in a single dimension, because we are only want to get the age as input, and we want to get only the median value as output. Okay, so it's one input and one output. So it's quite straightforward. It's a very simple. It's just a single neuron with one input and one output. And they were saying that the activation function that we're going to use is linear. Okay, we're going to see in very briefly what this activation function means. So let me jump back. Let me jump back again to the Keras API slide, and say that the activation functions are actually one of type of Keras models that we're going to understand today how they work. And we're going to see that there are some other laws of optimizers and metric models also important in Keras. So let me jump just right to the activation function. So we are seeing the example that we're going to use linear activation functions, which are the exact same function that we have seen in the example at the beginning of the presentation today, where we have input values, and we have a weight that multiplies this value, and then we have a bias that basically moves this slope here, this line. But there are many others present in the literature. I don't want to cover, I will not be able to cover in details. I will leave this slide if you're going to take a look. In general, you can see that the output of many other activation functions remains between -1 and 1, or 0 and 1. And then the weight value and the bias value basically moves this activation function to the left or the right, or basically change the slope in this case of the linear function would change the slope of the linear function, right? But we're just using linear equations here. So let me just go through this. So we have just defined our layers. We have defined the activation function of our layers. Now is the model that is the moment that we want to define how this model is going to be trained and how this model is going to be used. So we have the structure of the neural network. We have the activation functions. We have all the structure already set. And now we want this model to learn something. So this is where we run into optimizers. And this is what we're doing here. So this part is part of the compilation of the model. Just the compilation of the model is just model.compile. And when we do this compilation of the model, we need to define a few things, not much. Just one of them, and very important one, is the loss function, which is how are we going to measure how accurate this model is behaving during the training phase. The way of doing this is, in this case, we're going to be using the mean square error function, which is basically an estimation of the error of each of the samples that constitute the data set that we're using here. We're going to be using a steeped gradient descent, stochastic gradient descent, algorithm, which is the optimizer, which is the strategy that Keras will use to shuffle all this input and output data and iterate once and again over this data set so that we can make a good guess of what are the parameters that are within this model. And in this case, we only have two parameters, right? So we have one weight and one bias, because we have a single input neuron and a single output neuron, okay? And then we define some metrics which basically defines the let's say the effectiveness of the model, how we're going to evaluate this model later. So I'm going to skip this. So basically, this is what's happening here on the model compile. And up to this point, nothing happens, right? So this is just, we have defined the model, we have defined how the model can be trained, what is the strategy that we want to use for the model. And then what basically remains is just fitting this model. It's just say, okay, now you start and use the data that we have parsed from pandas. These are the two data that we have here. So we have we pass the values of the data that we have captured, and we have passed a few elements here to, let's say, configure this fit or this training phase that we have, that we want to proceed with. I'm going to briefly mention what an epoch and a batch size is. So an epoch is, let's say, how many times I'm going to go over the full data set while I try to find the weight parameter for my model. So in this case, I think that I'm going to run 5,000 times over the whole data sets. And we said that the data set is actually composed of 500 and something samples. And we're going to analyze these samples in batches of sizes of 32. These are typical metrics for this type of models. And I'm just going to run this to see how this looks like. I'm not going to run 5,000 epochs. I'm going to just run just 1,000 just to see how this looks like. And I'm going to run this example here so you can see the output. Sometimes it takes a few seconds after running the Tensor Flow. And we can see here that this is the moment where the model is being trained. So this is a moment where Keras is actually running over and over the data that we have and trying to make small changes to the model parameters so that we can minimize this error function on the output, and namely able to get the new an accurate model for prediction. And this is what we get after 1,000 epochs, which is not too much, but let's see, and this is where I think that visualization can play a very important role in this. And we can see that the mean square error in this case has gone down as we evolve through the epoch training, right? And actually continues to do so as we move on this x-axis. So this means that the parameters that we are successfully, let's say, sequentially finding are actually better and better as we move in this epoch. This is thanks to the stochastic gradient descent algorithm, which is the smart way of doing this, as I mentioned at the beginning. We can see that there are some spikes here anyway. So this is because this is there is no, let's say, known way of going to the exact optimization point, right? So this is like a guessing, and this is a search function that sometimes makes some wrong decisions and try to recover afterwards. But on average, in the long term, this should go lower, and therefore getting let's say a lower error as times goes by. And we can see here on the right-hand side that this red line that we have plotted here is actually the model of that we are training at this moment, where we have a bias, which is this distance, right, of the altitude of the curve on the y-axis, right, and the slope of the line is actually the weight of the neuron that we're using. This is why I'm choosing such a simple model, because it's just by a linear function we can see how these weights are being computed, and we can see that somehow this line tend to follow the trend, right, that we are seeing on the data set that we have. So this means that now we can use this red line to say, okay, if I have an housing of 25 years of age, then it's quite likely that the median value is going to be 15, for instance, in this case. Well, not so true, actually, because if we see, this is not really the exact behavior on average of the data set that we have. And the reason for this is that we are not running so much epochs, on the old training was really short, because we're not running this, we're running this in real time. In fact, what we typically do is say, we want to run this on 5,000 iterations, but in order to save some time, I'm just going to comment this line here, and I'm going to just configure the weights directly in the model, right? So I'm going to just taking out here is saying, instead of training my model, I have saved my previous training for much more epochs, and we can see that here we have a weight and a bias set here, and we can set these parameters directly to the model instead of training that from scratch. So if I just run this again, let me see if this works. oh yes, I think I need to comment one more thing here. Just want to come back to this data. All right, so if you take a look at this new training model, we can see that actually, if we leave this model training for longer time, we see that the slope actually now follows quite better what is the data set that we have, and then we have our single neuron network model working and trained and fitted to the data that we have. Okay, just going to close this. And also, I'm going to share the code afterwards, but we can print the output of the model, and we can see that the mean absolute percentage error metric that we have for the model here on the lower part is actually 26%, which actually means that on average, the prediction that the model is going to do is on average 26%, only has a 26% of error, which is not so bad considering that this is a very simple single neuron model, linear model for the data that we have. Okay, so I have a few slides with more detail about the loss functions, about the optimizers that we can use for this. But I'm going to skip this so we can get to the part where we discuss a little bit about how can we containerize this and how can we use this in real life. So I'm going to skip this, and this is what we did the fitting part, and this is what we had just seen on the resulting of the training model. And this is the history of the training of our model as we run through 5,000 epochs, and we get to this more nicely looking model here. Okay, so just to close the machine learning part and go into the containerizing part, what I want to say is that, as I mentioned, the step that we need to follow our data preparation. This is likely the most time-demanding part. I insist on this. And then we have followed the following step. We have compiled the model, right? We have defined our layers. We have defined our activation functions. We have defined our loss function, which is how do we measure the error from the model during training. And we have defined this stochastic gradient descent algorithm so that we can search through the parameter space in a smart way, right? And once we have compiled the model, we have fitted the model to the data. And this is the training phase where we have our machines going over several epochs of the data set and trying to guess which are the best parameters for our neural network. And then we have evaluated the model in the sense that we have seen that we have around 26% of error with the training model that we did. And using that line that we got, we can just simply make predictions of data values that are not present in the data set, right? And have a good idea on how or what would the price be of some of this house given a certain age that we're going to use here, okay? And the final step of this is natural for any application is, are we satisfied with the result, with the evaluation result? Or you can, maybe 26% is what you want, maybe it is not. If it is not, then this is the opportunity just to go back and iterate again and define a different layer configuration, a different activation function, and iterate again and try to get a more efficient model for the problem that you want to do. Quick last comment on machine learning here is that these are borderline chaotic systems. So we have so many parameters into play, so many possible configurations, and everything is so dependent on each other that every time you change something, then the results is dramatically changed in general, right? So the general advice for machine learning programming is to make baby steps. Step by step, make changes and see what happens. Do not change layers, configuration, and activation function at the same time to see what happens. Otherwise, you will really, really get lost very quickly. Just make small steps and updates. So make this to have your application up and running without major drawbacks. Okay, so I'm a little bit behind schedule. Maybe you're going to, if that's okay with you, I'm going to take around 15 to 20 more minutes to talk about the second part, so that I can comply with the percentage I mentioned at the beginning. We're talking about 80% of the time, 70% of machine learning, and the remaining part of how do we containerize these applications, and how is important the infrastructure that is supporting machine learning applications. So maybe you're already familiar with this, but if we want to run this application, this Python code, for instance, that I have just shown, then we typically will not run this just on a computer, right? On a simple server. We want to somehow isolate this software and run this in a very friendly and very controlled environment in such a way that we ensure that this application will run as expected in a very stable and let's say reliable infrastructure, so that we can let's say, for instance, in our case, provide some predictions, right? So one way of doing this, and was a way for several years now, was using virtual machines, right? Where we, on top of a given operating system host, we run some guest operating system with the library and the application we wanted to, and these, let's say, violet color boxes that we have here were fully under our control, and we were fully, let's say, ensure that this was the library that we were using, the configuration operating system we were using was right, and this was running on top of any hardware or any infrastructure. But nowadays we're moving toward what's called a containerized approach, where actually instead of running a guest operating system in a virtual machine, we are just running a container, a Docker container, as are known nowadays, where instead of having a guest operating system, we have what's called a container runtime. And we still get a stable configuration because we can control the runtime very well. And we can also control very well what are the libraries and the model and the rest of the environment of our code. And therefore, this is where Dockers come into place. And the result is that we have lightweight images for this. It's very handy, it's very practical, much more practical than virtual machines. And this is what's actually happening. How do you typically deploy an application nowadays? In this case, what I'm going to just briefly go over another demo I have for this, very, very simple also, I'm going to go over this very quickly, is I have a server.py here, which is an example of how we would use the machine learning application we have just used. So before jumping into this, let me say that in the model.py, at the end of the model that we have just seen, I'm just saving this model. Keras allows me to save this model. So I'm just saving this housing.model thing here, which is one of the files that we have here. I'm going to just click this and open just to see that this model, this is a binary encoding that's called HDF, and this is a particular type of coding. But what I want to say is that the model that we have trained is saved in this file. So what I'm going to do is say, well, I actually want to put a server in that provide my users a way of using the model that we have trained to predict the price of the house, okay? And thanks, we are using Python, and we are using, I have created a very simple Flask server application. So for those that don't know, Flask is a framework for creating web services, very simple. What I'm basically doing in this code, without going into too much detail, is just I'm creating, creating a Keras model from scratch. But instead of defining the layers, of defining the weight and training the model and so on, I'm just saying, hey, you know, just load the model with the information that we saved from the training phase, okay? And once we get this model loaded, we are going to just run a very simple HTML web interface to load this data and predict which is going to be the median value. This is very, very rustic HTML thing that I'm going to show now. But before doing this, what I want to say is that let's say that this server works okay and we have tested in our machine, and we just want to deploy this into a Docker container. So for this, we need to create what is a Docker file. And in this Docker file is what defines a container. In this case, in my Docker file, I have just loading an existing image from a Docker. And this is what makes Docker so powerful, is that we just load a Linux machine with the Python code and the Keras version that we just want to From this, I'm just saying that I'm going to run my application within this image very easily in this simple text file. And what I'm saying here is that I'm going to be, when I create my Docker image, I'm going to be exposing port 5000 in this case. I'm going to be creating a /app directory here, and I'm going to copy what I do need for my server. I'm going to copy the server.py file with the Flask server. I'm going to copy this very simple HTML I have created, and I'm going to copy also the model results to the container that we are creating here. And then on the creation container, we're going to install Flask, and then leave a command there where we run the server and make it run. So what I'm going to do now is just I'm going to move here to, I have a virtual machine with Docker in here, this case. And we can use here Docker commands just to see what's happening. And I'm going just to, so we can see that we are stepped on the same directory that we have here. We are stepped here. And we see that we have this Docker file right here. Let me see if we have got installed here. Right, so this is the same Docker file that we have open here, and we have it written here in Visual Studio Code. And we're going just to compile this image, and we're going to create this, and we're going to deploy this. So let me just briefly copy the command, just to make sure that I'm not making any mistakes. First, I'm going to run docker stop server. Okay, just making sure that it's stopped. Okay, and now I'm just going to try to copy this here and run docker run. What I'm doing here, just making sure that everything is correct, is that we're going to use this Docker file to create a Docker image with this very simple server with our machine learning application, and we're going to name this server. Okay, just going to click enter, and this is, oh, sorry, Docker build was already run before, and we're just running the image for this, and this is a Docker that is already running at the moment. Let me just check this. Okay. And we are seeing that actually we have our Docker image that was created using this Docker file, using the Docker build command. And this is actually running in our Docker environment at the moment. And what I'm going just to do is just go into my local browser here and just basically type in the address and the port that we're using. And this is a very simple HTML I have created in my server.py, and just using some input data or some ages here. And this is the age that I want to guess. And my server basically is making the prediction for, let's say, a housing of 25 years age actually has a median value of 26.4. And if we go to our presentation, actually, let me just jump back here. This was somehow what we were looking at here, right? So 20 for a, sorry, was a 25 age, we are getting something like 26 price, right? So this is very simple application example I'm just trying to show here from a simple server that actually uses the result of the model, the machine learning model that we're using here to predict a given number and use this as a service, as a very simple and rustic service anyway. In a containerized application, and this is containerized, and therefore this is in a control environment in the sense that we are using our Docker file with the image of the Docker that we want to use with the given library version that we are just installing here. So this is a fully controlled environment and very easy to manipulate, right? So this is what we're seeing in the presentation that we saw here. Very simple example. I just leave also a slide here. I'm going to leave this at hand if any of you want to try this. I didn't run this to save some time, but actually once you have the Docker file there, you need to build the server and then run it, right? And this run command, what we are saying here is that we are exposing port 5000 and using TCP IP, and we have some console output here. This is what this means, and then the server name is server name. And this just run the server in our Docker infrastructure here, okay? And these are just some notes on the commands that we have used on the Docker file. So going back to the machine learning container concept. So what we have done in this very simple example and stupid example is train and serve, right? This is what most traditional machine learning approach looks like, in the sense that we train and then the model and then predict the model in two very distinct phases, right? So we created the model, we trained the model, we save the results and the weight on the model, and then we use that saved data in our server to make predictions. So predictions are not compute intense, at least let's say got this compared with the training phase. So the training phase is the heavy workload that happens over the data set that we have, and then the service part actually comes afterwards, where we are actually predicting, making the actual prediction. But there is like an alternative machine learning approach that's emerging on the last year, which has different names, but I like this one, which is continual learning, where somehow these training and service phases are actually more intertwined and more interdependent of each other. And in this continual learning approach, machine learning models are basically continuously being updated with new data, right? And this has to do with more challenging applications where you need also to adapt and change your model as you start to get some more new data inflow in such a way that the predictions that you're doing actually matches the latest observations. And for instance, in the example cases of the housing prices that we have seen, obviously I'm stressing the argument here, but we can say that as times goes by, the prices changes, and therefore we want our model to be trained in a continuous way and somehow weighting the latest observation a little bit more than the older one, which is what we do want to do. But this actually challenges the very simple approach that I have used a few minutes ago, where I have a server that loads the model and provide the data prediction out of that, right? So this also challenges the containerizing, the container approach, because we don't no longer have these two separated phases of training and serving, okay? So this is one of the challenges that we have that basically adds to what is the machine learning pipeline that we have simply, let's say, overlooked in the example I shown, because it's very simple. But there are so many other steps that need to be played, that must be handled on place, which are the data ingestion, how do we get the data, how do we analyze the data. We basically cover the data analysis steps in the visualization part with Matplotlib in the example we have seen. The data transformation, we need to adapt this data to normalize this data such that it serves the model. Data validation, model building, we have did this in the example, train the model, validate the model, train model at larger scales with larger data sets, and then serve the model and monitor the service. So this is an extended pipeline that also needs to be considered in larger machine learning applications. And this is where containerizing techniques actually comes into place and can serve and facilitate of this, all these tasks in the pipeline. So for this, Kubernetes is just the right approach for this. Kubernetes is like an evolution from Docker, namely just instead of having just a single Docker that, as we did, just put this in a Docker runtime and just run the Docker image as we did with our server in this webinar, we can have a Kubernetes cluster where actually we orchestrate several containers, okay? Several Docker containers. And we can have a container for training, and we can have a container for serving, and we can have a container for parsing data, and we can have a container and so on for each of the data pipeline of machine learning application. So we need Kubernetes for having this. And Kubernetes is an open source software provided by Google, and it's highly configurable and actually some quite complex infrastructure to be made based on this. As I mentioned, different containers somehow interconnected between them and acting in a cluster approach. And Kubernetes are defined in a YAML file, which is somehow similar to the Docker file we have seen, a little bit more complex because it's like a Docker file of Docker files, to say somehow. You are just defining a cluster that actually runs all these Docker files. Something interesting to see from Kubernetes is that we typically have like a master node that takes care of coordinating worker nodes, which are actually the ones that carries the most of the heavy load. So for instance, we have a worker node for training, a worker node for prediction, and have all this integrated into an Kubernetes environment. I will leave this note here for further inspection on your side, which is Kubeflow. Kubeflow is a specific Kubernetes framework for machine learning that somehow is already tailored for machine learning pipelines. So everything that I mentioned here, just training the model and prediction and getting data prepared, getting shape, and so on. So we will likely like to make another webinar on Kubeflow specifically because I think this is quite interesting to see. Otherwise, I'll leave this note here for you to inspect as a very interesting alternative for containerizing machine learning applications. But even though Kubernetes is a good fit for what we're trying to do, there is some further let's say aspects that need to be considered before deploying a successful machine learning infrastructure. Okay, and this has to do with different aspects. Let me just briefly discuss this. So, for instance, in the image registry, right? So we have created Docker images in the example, and we have just run it. But in practice, you need a registry of these images, which is like correctly versioned and so on, and you want this to be private in many cases, not to be public. This is especially if you're running a commercial application and so on. And then you need some data management also approach that can help you in handling the data and the potentially very large data sets that you're going to use in your machine learning application. You are likely going to need some dedicated hardware, right, for this. So we mentioned that Keras is very well suited for GPUs, and also you will likely need some substantial storage for handling your data sets, right? There is also like a life cycle approach that needs to be taken care of. We're talking about how do we create, how we scale this application. We want to scale training processes. We want to upgrade our Docker to newer and updated versions. We're going to keep track of these versions quite closely, and we want to make a very good follow on how our model iterates along this, let's say, distributed infrastructure. We do care about availability aspects and just our model to be, let's say, continuously available when needed. We do care about monitoring the operations of this infrastructure, of the machine learning infrastructure, and we naturally care about security of how all these Docker images are running in our infrastructure in a safe way, that access is properly restricted, and we naturally take care of sustainability and how this infrastructure that takes so much processing power actually maps into an ecological footprint that we want to take a look at. So these aspects are not solved by Kubernetes, right, by default, but they are solved by what's the managed Kubernetes approach at Cloud&Heat, what Cloud&Heat is offering. So even though the managed Kubernetes product on Cloud&Heat actually runs on Kubernetes, there is a quite significant added value on all these aspects I have just mentioned that are really important for deploying successful machine learning applications, such as the one that we're talking about today, right? So this is why I think that the managed Kubernetes is something really important to look at, and basically a very good way of just focusing the machine learning development on the machine learning aspects, which are already complicated, as we mentioned, and not on these infrastructure topics that are already taken care of by this service that Cloud&Heat offers. And most importantly, I think that the managed Kubernetes is a keystone in the long-term vision of Cloud&Heat, which is distributed data centers. As I mentioned earlier at the beginning, Cloud&Heat is focused on making a recovery of the waste energy that is provoked by all these compute-intense jobs that runs on data center nowadays. And as machine learning applications are being deployed massively, and as we are seeing all these continual training approaches for machine learning, where we're going to have or model being trained continuously via these stochastic gradient algorithms that basically uses trial and error and so much demanding processing and demand, then we're going to be just wasting more and more heat that's produced by the data center where this infrastructure are executed. Okay, so this is where the Cloud&Heat visions actually comes into play and say, hey, you know, wait, and we can be a little bit smarter about this, and we can save money if we just use this heat in an intelligent way, for instance, to heat buildings, or for using this heat into power plants, or just by choosing a very smart, or in a very smart way, which data center is going to execute the computation of the training, for instance, in such a way that we're using a data center where we have some available energy that is being unused at any given moment, and so on. And we can take all these aspects into consideration, such as cost, for instance, regulations on where can we run a given process or not, what is the latency that we can tolerate to access or particular Docker container that we have just deployed, for instance, what type of hardware do we need, such as GPUs and so on, and also the ecological aspect that we have just mentioned, so that we can be, let's say, smart in deciding on which data center do we want to run or a compute-intense machine learning application. And this is what Managed Kubernetes and Cloud&Heat operational infrastructure actually allows us to do, and basically let our effort be focused on the machine learning implementation, and let all the infrastructure, let's say, important components, such as the one I'm mentioning here, being taken care of by Cloud&Heat and the managed infrastructure, managed Kubernetes over this distributed data center infrastructure I am presenting today. So I'm just closing my talk with this, and I hope you enjoy the path of going over machine learning applications. We believe that machine learning applications will be more and more important in day-to-day life. And we at Cloud&Heat are somehow presenting this vision of the future of compute in the sense that we are going to see distributed data centers, and we are going to need some smart way of handling the data workloads into this distributed data center in such a way that the heat and energy is used in a very smart way. And we invite you to take a look at what we're offering at our vision in such a way that you can deploy your machine learning application with us, considering all these economical, technological, and ecological aspects we have just discussed in these very last minutes. So without further ado, I will leave just here my contact, my email, and I will just briefly go over the chat window to see if there is any questions, and please feel free to ask at this moment. So I see there are no questions. So with this, I'm basically leaving you my email. Please feel free to reach me if anything, any questions or any consultation on this. We're going to public this video for later visualization if needed, and also sharing the example codes that we have seen on this machine learning tutorial that we have today. So with this, I appreciate your time, and well, I wish you a very good day.